Hi, hello everybody, GreatCorn here, and I recently made a 3D horror game using assembly. In this video, I'd like to explain the development process, some inner workings of it, and generally the hell that I've been through. When working with assembly, a lot of things that many modern programmers tend to take for granted have to be recreated from scratch. Concepts must be stripped down to the core functions and defined explicitly. So let me do just that on my previous statement. I have made a 3D horror game using assembly. Herein, the word made implies me creating the game, not only regarding the code but also the assets, such as textures, models, sounds, possible music, both incorporating said assets into the code and making them structured around the code in some ways, and combining this all into a package that has at least some redeeming gameplay qualities and aesthetic consistencies. Bear with me here. So now that we've got that out of the way, let's get to the conceptual qualities of the game, the 3D and horror parts. 3D means three-dimensional. Applying it to the context of an interactive medium such as a game may mean two things. First, the game presents such visuals that the player is able to interpret the image displayed on their two-dimensional screen as a projection of a three-dimensional environment, which I would classify as visual 3D. Second, the game operates in the 3-axis, all of which may be actively used throughout for different applications. For example, movement on the 3-axis, the incorporation of realistically simulated gravity and physics, positioning interactive game elements in the 3D space, and more. This I would classify as functional 3D, which most often incorporates visual 3D for the sake of clarity and familiarity. Many modern game engines offer true 3D capabilities, that is, both visual and functional 3D, with the usage of modern rendering APIs, such as Vulkan, DirectX 12, and OpenGL4 Core, while also giving the ability to use real-time rigid body, soft body, etc. physics simulation. My game engine is Notepad++, coupled with a Microsoft macro assembler and linker, which will bring us to the last part of my statement. Before that, to clarify, even though my game uses visual 3D elements as a cosmetic function, it doesn't really utilize the third or the second in the 3 axis from a gameplay perspective, making it a theoretical 2D game. A horror game, well, is a video game genre that is structured around trying to scare the player and generally the feeling of fear. This is probably my favorite genre to explore, and I feel most comfortable making the same freaking game over and over again. I said that I made the game using assembly. However, in reality, it's quite a bold claim that practically means nothing. Let me explain. Assembly is not fixed like C, Pascal, or any other widely used programming languages. The exact syntax and sometimes even major details vary, depending on the target computer architecture or operating system. It is intended to be a more human-readable version of pure machine code, ideally translating directly into opcodes. In a crude simplification, assembly is a way for programmers to almost directly read and write whatever mess of data is in your everyday executable files. In a way, assembly is the definition of the opposite of cross-platform. So, with that out of the way, which assembly do I use then? I guess it would actually be accurate to rephrase my statement to I have made a 3D horror game using Windows, but that only obfuscates it further. Windows has plenty of assembler options to choose from, such as FASM, NASM, MASM, TASM, you get the idea. In today's terms, many development environments and programming languages try to be as cross-platform as possible, for example, translating our favorite print command into lower-level system procedures, which in turn, at least after a couple iterations, get to the central processor unit and play around with it. Taking this as an example, when writing assembly, I have to consider that I don't have any fancy print function available, and instead, using the Windows API, have to get the command line handle and output some stuff into it from a preformed, preloaded buffer. However, actually, with MASMZE, that isn't really the case, as it contains many, barely if at all documented, macros that are designed to ease the use of assembly and help programmers get into it, though that still doesn't drive it very far away from any x86 assembler syntaxes regarding the explicit nature of coding in it. Now, I just want to clarify that this whole thing really isn't a breakthrough, and similar stuff most definitely has been done before. Personally though, I feel this is a big accomplishment for myself, for the sake of my programming skills and understanding how Windows, programming in general, compilers and processors work, along with studying OpenGL and 3D graphics. I feel that it was good for me to abandon a lot of the bases that I could previously rely on, like an engine or a sane programming environment, and try to construct something almost from scratch. Many game engines nowadays offer completely or almost scriptless solution for game development to assist beginners in getting into the industry. The minimal coding allows for easier scene manipulation for the developer to easily project their artistic vision. Some engines even offer their own asset marketplaces, which can include script modules that are built around the engine and may help solve certain tasks. The development environment that I chose, however, doesn't really have these capabilities and, in contrast, relies on constant coding. This means that the scene's objects and their visual appearance have to be set up and coded in manually. This, along with the previously mentioned nature of assembly, where one higher language operation may have to be split into a dozen of them, makes the development process pretty harsh and slow. However, the inclusion of libraries means that stuff like OpenGL, coupled with it not being object-oriented, doesn't really differ in its usage from other programming languages like C++. So, we finally finished decompiling the subject of this video, but not everything is clear yet. I had a goal in mind, to make my game as native to the Windows API as possible without the usage of external libraries. Another bonus goal was to make the game optimized enough to run on lower-end devices and to keep its size as minimal as I can without really focusing on it, as I didn't want to delve into the different file formats and compression algorithms yet. Sadly, I didn't exactly deliver on all of those goals, and in some instances I cheated a little. With the usage of MASMZE, I was granted many macros that I didn't refrain from using. That includes conditional directives, while loops, invoke directives with procedure blocks, local variables, and most importantly, the print macro for debugging. Nonetheless, many experienced programmers will understand my pain of working with assembly in any form, and experienced assembly programmers will laugh at me and tell me to do everything on an 8086 with pure opcodes. In terms of libraries, I mostly use the DLLs that come bundled with Windows. MASMZE has a lot of header and lib files also included with it, which greatly simplifies the process of importing standard Windows libraries. That includes OpenGL, the rendering API which I used for the display of the 3D graphics. I also used a little bit of GLU, the OpenGL utility library for certain procedures like making projections without defining matrices and their operations. My hopes for everything being relatively fine without the usage of external libraries shattered when I got to implementing sound. At first I was experimenting with the Windows Media Control interface to play MP3 files, however performance-wise it wasn't very good, and sometime in the development I found out that the MP3 format used to have a very costly license and some people are still unsure if it's free to use or not. So, with both not wanting to use uncompressed WAV files and still feeling the need to keep the quality high enough, I opted to switch to my favorite audio format to use in game development, OGG Vorbis. I found the libOGG library on the official site along with libvorbis and vorbis file and barely got it to compile with zero knowledge of what CMake is. All I needed to do was to decode the OGG audio files into pulse code modulation data. And libOGG, well, being the official solution, was kind of overkill for me, together with libvorbis attributing a whopping 700 kilobytes to my project. Then I accidentally stumbled upon Sean T. Barrett's collection of public domain C libraries, which included a library for decoding OGG vorbis files. I quickly got it to compile into a nice single 100 kilobyte DLL file using the GNU-C compiler. Then I needed a reliable way to output the audio data. Windows offered me a variety of options, including Wasapi and Xaudio. It also has a multimedia library built in which contains an interface for this task, the WaveOut, which was the closest I got to playing the OGG files using pure Windows. However, the API ended up creating more problems than solutions, kept crashing, and offered a single volume control for the entire mixture. So I cheated again and switched to OpenAL instead. I wrote custom headers for it in the best way I knew. Coming from Pascal, I never really got into what static linking and lib files are. The use of OpenAL allowed me for extremely easy audio control and 3D positioning. There, I guess I have confessed all of my sins regarding me straying from the true path. Now to my sins in the code. Well, actually it's pretty chill at the beginning. The basic premise of the game is a generic first-person maze runner. MASMZE provides a random number algorithm, so I didn't need to implement my own to use for the randomness of the maze. I was able to organize all of the initialization, rendering, logic processing, and resource disposal into neat procedures thanks to the macros. The maze algorithm is quite simple, basically runs a tree of squiggly lines that create walls around on a grid until they fill all the spaces. Then the grid must be displayed as a closed 3D environment with, at the very least, walls, floor, and a ceiling. To do that, we must first acquire a window. Using pure Windows API to do that gives us a miniature wall of code, but other than that, it's very simple. We set up a message loop to get the messages sent to our window by the system, and effectively the user, and make a message processor. In it, if we catch a paint message, we shall render our scene, and don't send the default message to the window, for the system to continuously send us more paint messages, creating a render loop. We also could put the render invoke into the message loop instead. Before drawing anything upon the Windows creation, we must also initialize OpenGL. I use the fixed OpenGL pipeline for the sake of simplicity, totally not because I spent like a month working on a game engine in Pascal and tried to use the programmatic OpenGL pipeline and never actually managed to get anything to work. Compatibility? And to see what kind of stuff I could do with such limited technology. And also because MASMZE doesn't have headers for the stuff. The usage of this pipeline limits the functionality, but simplifies the coding process and helps with the optimization goal, being supported on lower-end hardware. This choice also made me opt for a pixelized low-poly aesthetic, which is overused in the indie game industry, but at least we're not overkilling it by using something like Unity. Next, in the initialization procedure, we enable a bunch of OpenGL's features like face culling, depth testing, lighting, fog, and textures. For the sake of organizing, I have created separate procedures for drawing things. Such is the draw maze procedure, which iterates through the previously allocated using WinAPI procedures and filled maze buffer, and based on the values in the cells, draws corresponding geometry. Did I mention there are no arrays in assembly? MASMZE, however, offers a comfortable implementation of structures to pass consequentially stored data, possibly of different sizes, to procedures, including the WinAPI ones. This is how we were able to register the window class, create the window itself, and set the pixel format for the OpenGL device context. Back to the rendering, in OpenGL there are different ways to draw something on the screen. I use OpenGL's lists to store mesh data and call them when I need to draw it. However, first we need to import our meshes, and since the size can be relatively big, it's generally not a good idea to store them in code. For that purpose, I made a simple file format that's pretty much the wavefront OBG, but instead of indexing different vertex, normal, and UV values, I put them consequentially and import directly into OpenGL procedures. This may increment the mesh size slightly, even though instead of human-readable data, I store the 4-byte float values directly as bytes, but in some cases with smaller models the size was smaller instead. For importing textures, I could use an imaging library. However, I decided to store raw color data in bytes in supported OpenGL color formats. Switching to RGB 565, 5 bits for red channel, 6 bits for green, 5 for blue, was an alright choice over BMP files, as it made it easier to import and lowered the size, while maintaining decent quality. In some instances, I used other color formats when applicable. The meshes were quickly made in Blender, and the textures I generated using Stable Diffusion with additional polishing by hand. Now that the meshes and textures are imported, we can assign the textures and call the OpenGL lists. However, before that, we must make a perspective projection to actually make sense of what is being displayed. That can be done using matrix operation, but I used GLU perspective, which takes double precision 8-byte floating point, from here float, values as arguments. As such, the arguments are double in their count, because we are working with a 32-bit application and the pointers are 32-bit in size. Having made the projection, we can position and rotate our meshes and draw them. The glTranslate and glRotate functions are one of the functions in OpenGL that have two variants, ones that take double precision float arguments and ones that take single precision. To operate with floats, we use the FPU, or floating point unit, operations, as they are vastly different from integer numbers in their storing and arithmetic conventions. Then, using Windows messages, we configure a controlling setup and we can finally roam around. For player collision, I lazily incorporated collision checking in the wall's drawing procedures. They simply add the player's velocity to the player position, check if it's in the desired range, if so, set the velocity to 0. Thanks to GJ2007 of the MASMZE32 community for providing a compact macro for float comparisons to make the code compact too. Another important part of designing a game is to work around possible performance differences on different machines or setups. Many modern engines provide something called delta time, a factor that we can multiply our movement on that scales according to frame rate. In my game, we calculate it using a high-precision Windows performance counter and compare values from 2 subsequent frames. The result can also be used in lerp function to smoothly and quite cheaply interpolate values. So we got the maze generation going and some basic player controls, We've also set up our scene to have fog and some basic lighting to make it look a bit nicer. Now we have to make a way for the player to complete the maze and advance layers. For this, in the maze drawing algorithm, we simply change the upper left and lower right walls to be doorways. The doors are then drawn as separate meshes to have a smooth rotation animation. The player has a player state variable for specific states like cutscenes, where we can code a nice exit animation. After it, we regenerate the maze with possibly changing its size. I've mentioned animation, and now would be the time to get to the features that explore this topic, but first, if you are somehow interested in the game itself, I must issue a spoiler warning. If you want to experience the game for yourself, you can download it for free from the itch.io page, granted if it runs on your PC at all, as the game has been known to be a little picky about where it wants to run. Before this moment, I've been talking about the more general stuff. Now, let's take a look at the maze's inhabitants and the way they function. The first monster you may encounter is this guy. I call him Wimblik in code, so I guess that's his name. Wimblik sports a generic uninspiring shadow monster design with a slender body, 2 glowing eyes and sharp claws. He, so far, has 3 possible forms he can appear in, on which his AI algorithm depends. The first form is a passive one, where he stands in one place and stares at the player. The common approach to visualize this kind of character and behavior would be to use skeletal rigging and animations. I simply didn't want to bother with implementing it all from scratch, so I opted for a Quake-like solution of vertex animations. In skeletal animations, the model is comprised of a mesh and a skeleton. The mesh is most often built out of points called vertices that connect in specified ways to create faces, or polygons. The skeleton of the model can have several bones that the vertices can be linked to with variable weights, to easily transform with the bone. This creates an optimized interface where the user has a more organized way to manipulate the mesh and create animation by interpolating the bone transformations which internally affect the vertices. This also allows for a huge range of movement and many possible skeleton poses, along with more modern terms like procedural animation and inverse kinematics. Certain older games like Quake used vertex animations instead, where the mesh's movement was stored in static keyframes, which were iterated frame by frame. This simplification meant that there was no processing power wasted on the smoother movement and armature calculations, but also limited that movement range to only the pre-made keyframes. In our case, that kind of diverse procedural movement is not really needed, and what this method offers is enough. In my personal opinion, the uninterpolated animation might amplify the uncanny factor of the monster's appearances, as it is known that the human brain may find unnatural movement like that creepy. Wimblik's first form requires him to look at the player, so we can simply make a frame of him standing and rotate it to look towards the player position using the arctangent FPU operation. However, I decided to make it a little bit more interesting and separated his head from his body, so that his body can rotate a little slower than the head and to accommodate for vertical rotation, calculated by simply using the distance between Wimblik and the player. But Wimblik doesn't calculate that distance just to rotate his head. Originally, he does it for something different. Yeah, sorry about that. Wimblik's second form is a lot more subtle. He waits for the player to stop turning around too much and appears behind them. If the player looks at Wimblik, he disappears. Normally, I would write a function that uses the dot product of the camera's forward vector and the normalized vector of Wimblik's position minus the camera position, but as Wimblik is already using arctangent to look at the player, we can simply find the difference between it and the player camera rotation along the y-axis. This wouldn't produce accurate results at variable distance, but here it is more or less fixed. Wimblik's third and final form is when he's free to roam around the maze. For this, I made a pretty cheap and dirty random navigation algorithm where if Wimblik is close to a maze cell center, he starts thinking if he can continue going forward, or if he should change his direction. His word float position is transformed into maze cell integer position, and he checks in random order if a cell adjacent to his current one is blocked by a wall or not. The order of the checks is slightly randomized, but the opposite direction of the current one is always checked last, to prevent him from constantly going back and forth. The randomized order gives Wimblik the ability to turn right or left, if such a possibility is presented. Regarding the animation, 4 walking frames are used and iterated with a timer. Wimblik also has a positional audio source tied to his position, which is, I don't want to say made possible, which is made easier with OpenAL. When Wimblik gets near the player, he starts having a strangling minigame with the player. The player dies if Wimblick pins them to the ground or if the screen completely fades to black, as it slowly does. Wimblick lies motionlessly after the player pins him to the ground. This minigame has Wimblick using a total of 9 animation frames plus the lying on the ground pose frame. The second monster you may encounter is none other than Kubale. This guy, along with his name, appeared in a dream of mine and wasn't much better looking there. Kubale has only one form, but so far 2 ways of appearing. The first one that you saw involves a set of operations with Kubale's state similar to how player state is used. The second way of appearing is it simply spawning into the level. Kubale is your typical SCP-173 or a Doctor Who Weeping Angel, meaning that it moves only when out of sight. Debatably. It uses the previously described dot product method to determine if the player is looking at it or not, and then moves, checking the maze buffer for walls and colliding, sliding along them. The collision implementation is flawed and might make it stuck in walls, however this throws it around a bit more, resulting in a chaotic behavior, so I'll call it a feature. If Kubale gets too far away from the player, it teleports into a random position in the maze a certain distance away from the player. When too close to the player and they aren't looking at it, Kubale starts inducing hallucinations in the form of Rorschach-like ink blots. The screen slowly fades, and if the player stands like this for too long, they die. Kubale doesn't really need an animation since we wouldn't be able to see it, however, Kubale has 4 keyframes with slightly random poses for a more varied appearance when the player looks at it after it was moving. The game is planned to feature more characters and monsters, however, as it is a passion project with pretty much no recognition, I can't really promise anything. Regarding the 2 monsters that are in the game now, they are able to spawn in simultaneously. So, as a form of simple interaction, Wimblick, when in his 3rd form and close to Kubale, just goes in the opposite direction. Supposedly. Now that the monsters are out of the way... what else is there? Oh, so with the limits of the old fixed pipeline OpenGL, there isn't much room for any visual effects. We can't really use frame buffers, we don't have shaders, none of that fancy stuff. We also have to keep the game optimized enough to run on an ePC, because we all know that it's the superior gaming platform.
This is literally an ePC and it's working at like, I don't know, 60 FPS?
This results in me trying to squeeze out as much of the basic stuff that I have as possible. The shadow below Wimblick is your standard blurred circle, some ambient occlusion is drawn on the environment and miscellaneous textures, the noise is just a static texture with a random offset drawn on the interface, and the rain from the janky intro is exactly that, but the texture is different. The game also doesn't use any dynamic audio effects like reverb and filters, though as I've read OpenL supports that, but the effects are all in the audio itself. The game also uses the per vertex lighting model, which is, as far as I know, the only one that the fixed pipeline supports, meaning that the light contribution is calculated per each vertex, instead of per each pixel, which may create bad looking lighting on low poly meshes, though it gives way better performance and doesn't look too horrible if subtle enough. So, you know the... One thing I should... Also, did you know that I had to implement my own bitmap text rendering function? I made each used symbol a texture and stored their paths in a file, separated with null characters, which brings me to how one of the most widely used data types commonly works, the strings. In reality, as I've mentioned, assembly doesn't have arrays, and what are strings but an array of characters, which in turn are numbers that are interpreted into a readable format by the system. Assembly, though, being a language where the user can manage their memory in a more low-level way, can allow the programmer to store certain values consecutively, or allocate a big chunk of space to operate using pointer arithmetics. A pointer is a specific value that represents the location of certain data, like a variable in memory. In a 32-bit program or system, pointers are 4 bytes in length, or 32-bit. Therefore, if we want to make a string, we allocate as much space as in the length of our string in characters plus 1, which would be the null character to terminate the string. We'll take an ANSI string, for example, where each character is 1 byte in size, as other encodings might have characters that are 2 bytes or more. When the computer reads the string, for example in a Windows procedure, it might not know its length, so it takes the address, reads what character is stored in there as the character size in bytes, meaning 1 in our case, and does the same process until the character is 0. So, yeah, the text rendering function, the game loads the symbols by their file names in the font index file and then iterates through the strings given to it and does the thing. I guess that's it. And also, did you know that can be it? That there has to be more. But I didn't waste an entire month for this little progress. I didn't have sleepless nights, because whenever I closed my eyes all I would see were registers, constant operations, moving from EX to EBX, from EBX to ECX, shifting the bits wherever, XOR ABX, ABX. I didn't have fucking dreams about the FPU operations. I didn't have insomnia because of the constant feeling that I have to initialize the FPU, pop the stack, or clear out the register, or load that FPU code, or use the OR operation on it, or to change the rounding mode. Guy, I didn't double, no, triple, no, quadruple check all the pushes and all pops to be equal so that I don't overflow the stack or mess up anything. I didn't check for memory releasing a load code in my mind. I didn't make the sure precision of ABX for nothing. For nothing. For this little. How the fuck did I move so slowly? This isn't impressive at all. This is just a bunch of bullshit and garbage that nobody cares about. I wasted my life. I wasted fucking time for nothing. Well, at least one person thought it was cool. In all seriousness, I did learn quite a lot while making this game, and I'm very thankful to anyone who tries that out and to you for watching this video. This type of videos isn't common, which I don't think it ever appeared in chat. Oh no, there's one. So yeah, I don't normally make these kinds of videos, hell, any videos, but if you liked it, then good for you. It also took me quite some time to make it, and I very much appreciate you watching it till the end. If I made any mistakes in the technical specifications or details, please let me know in the comments.
Smash that like button with a sledgehammer! Obliterate that subscribe button like the Hiroshima and Nagasaki combined were but a slight breeze! Hit the bell as hard as your drunk dad hit you in the face! And don't forget to donate all of your money to me, please, I need medication!
For legal reasons, this is comedy.